Dr. Sarah Demers, welcome to the show. I'm so glad
Thanks.
that you're
I'm
here.
really happy to be here.
Yeah, there's so much that I want to get into with you. We only have a short amount of time, but before we get into all of that, I would love to know the events, the pivotal events in your life that led you to doing the work that you're doing now with Yale and CERN.
I think when I can look back at high school at my very first physics class, um, I had always thought about myself as a humanities person, but when I took physics, it was so shocking and challenging and unexpected. I really was intrigued by it. And one of my teachers, I went to a very small school, and at the time, my math teacher was my English teacher. And he said to me, "Have you ever considered being a research scientist?" And I think that was really what got me thinking of this as a possibility. And when I went to school as an undergraduate, I had a work study position. I started out working in the library, but my sophomore year got a position working with a physicist doing research. And I admit I expected to really hate it. I didn't know what research was. It sounded probably awful and boring and lonely and sterile. But I tried it and absolutely fell in love with it. So I guess I haven't looked back since that first research experience, which was in particle physics. I was working on a detector. So yeah, I jumped right in.
Yeah. And that leads us perfectly into what you're doing now, working with the Atlas project for CERN. I think a lot of people don't realize that there's different projects all coming together for the same mission, but you need those separate projects to measure and to really back up what everyone else is finding. So can you talk a little bit about what its mission is specifically and what it's looking for, especially ahead of the restarting of the accelerator on Tuesday?
Absolutely. So Atlas is one of the general purpose experiments at CERN. There are two of them. That means we have a very broad physics program. Over 1,000 papers have been published so far on Atlas data.
Mm-hmm.
So we are looking to better understand what we have already measured, the particles that we understand around us. We're trying to really get a better handle on the Higgs boson particle, which we discovered in 2012. It's still mysterious enough so that it requires a lot more study. And we are also looking for a host of other possible things out there that we haven't had the energy or the data to see yet. And that's what's most exciting about this upcoming run, is that we're going to have our hands on a higher energy, more energy to work with, which means that it's like you're climbing up to a taller mountain and you can see further. There's just more area that we can explore. So it's a really broad research program.
Yeah. And it seems like, it's been shut down for 3 years to do upgrades and things like that. What is the reason that there is that rest period? Is it to get, I don't know, just explain it to us for the people who don't really know, who don't have the physics background.
So it's probably worth saying that the Atlas detector is 6 stories high. It's the length of a football field. It weighs as much as the Eiffel Tower, and it has hundreds of millions of electronic channels. So there are over 3,000 of us who are working on this detector, and just keeping it going, keeping it running takes a huge amount of effort. After a period of running, the radiation levels are pretty high. We have lots of particles that are created, and so some of the electronics get damaged. And so we have to replace things just as part of the normal life cycle. But then we also have this example where the Large Hadron Collider itself, the accelerator that provides these protons to us, becomes more powerful. And so Atlas has to up its game. We have to react. We know we have higher energy coming, more intense beams coming. We have to make improvements. The detector is 100 meters underground, and taking it apart, this massive machine, making sure all of the cables are done properly, all of the wiring works, implementing new technologies, testing new ideas. this does not sound glamorous, but it's a serious logistics problem. Our spreadsheets are
Yeah.
magnificent, just to get this project up and running again and cope with the data and have access to the physics we want to explore.
Yeah. Was there a point where AI and big data kind of hit an inflection point where you could research and understand all of the massive amounts of data that is now being, is now coming through or will come through? I mean, I feel like AI kind of was going like this, and then all of a sudden it was like that. Was there like a specific year where finally you were like, okay, now we can organize this and understand all this stuff that's coming through?
I think it's been a partnership. It's a transition that started a long time ago. We needed, as early as 2001, to use some pretty sophisticated machine learning techniques to untangle some signals. You could say that we're both driven by desperation. We have no choice if we want to extract as much out of our data as we can. But also, I find that the students I work with now are so excited about machine learning and this ability to extract more from the data, the creative aspect that it comes with. So we're being pushed in that direction by our requirements. We're being pulled in that direction by the intellectual curiosity surrounding it. And I can't point to a year, but I just was reading a list of thesis projects that have come out in the last month on Atlas, and 3 of the 5 had machine learning right in their titles. So it's everywhere now.
Yeah.
And it's definitely, a lot of excitement around it for sure.
Yeah. What do you think it is that gets 4,000 plus people from all over the world to come together to work on a massive undertaking like this, to mess with the wires and the data and the research and to write these papers, like all different aspects coming together for one purpose? What do you think it is that draws the attention, that draws the love from so many people?
It's remarkable that it happens. I thank you for asking the question. I think it's worth acknowledging because we're not a business and we don't pay each other. It's amazing that people with such strong personalities can accomplish this feat that's so collective. I think that we're doing something that's so basic as humans, trying to understand the universe. We're asking really fundamental questions about what are the particles around us? How do they interact with each other? You feel like you're part of an inquiry that's been going on since humans have started looking up at the sky and wondering how things work and what's out there. So I think the questions have that drive to them, that feel there's a purity to it, or an excitement to it. And then to be a particle physicist, you have to be willing to, in these big collaborations, be one of thousands. Our names are in alphabetical order in our papers. So there has to be at least some ego compressing, right, to be part of this. And for me, something that keeps me going is to not let down my colleagues. We all have to do our jobs very well. And my colleagues are my friends. We're working together on something that really feels like a mission. It's an incredible challenge. It's exciting. We don't know what we're going to find. And just one last thing, because I could go on about this forever, but I also love the fact that it's relatively flat in that I have colleagues who are 18 and just starting as undergraduates, and I have colleagues who are past retirement age but can't pull themselves away in their 80s. So that's also wonderful to be part of that community where the exchange of knowledge and work together has to happen. Of course, we have challenges and frictions and arguments. But at the end of the day, we all want to discover the physics that's out there for us to find. And so we find our way to compromises to make things work.
Yeah. And what are the implications of finding, antimatter or dark matter, things that we theorize exist, but we've never actually measured? When that starts coming through, when the data starts saying, yes, this is a real thing, what does that mean for the rest of us in the world and where we're going in the future?
That's another good question. I think antimatter is something that we're coming to better terms with in a number of experiments. We actually produce a lot of it at CERN. You bring up dark matter, right? There are some really big mysteries out there. I think, again, you can look at this in a number of ways. It means if we take a step forward that we better understand our universe. And that's the main goal, right? Then we can ask the next set of questions. We also have seen, as we push forward in this work, because of the complexity, the amount of data, the rate of the data coming in, the kinds of technologies that we need for our detectors, as we move forward, we push other technologies forward. So we would call that technology transfer. I think there have been a lot of benefits in the field of diagnosing and treatment in medicine. When you make progress in particle physics, some of that transfers out, right? But it's hard to know. When the electron was discovered, that was not at all a practical discovery. That was a magical, what is this mystery? Let's try to uncover it discovery. It's impossible, I think, for us to predict how what we learn will show up around us in the world in 100 years. So the basic question is, moving forward, there's a director of the National Science Foundation who said, we have to always be pushing out on the frontiers of knowledge in all directions, or we'll never be able to solve tomorrow's problems because we don't know what those problems will be. I also find that very inspiring.
Yeah. Yeah. I mean, is that what drives you in your work each and every day? I mean, with anyone with a job, career, it gets tiring sometimes and you don't know if you want to get out of bed, but what is it that gets you motivated and passionate? I mean, just talking with you, I can see how much passion you have about this. What is it about this world, this unknown, that keeps you going?
I think I just, I wake up sometimes when I'm based at Yale in particular at, 3:30 in the morning to join a meeting. But even in those instances, I feel really grateful that I have this opportunity. I know that I just feel really grateful that I can be part of this group, part of this team. I'm very lucky this year to actually be able to make an important contribution with getting ready for this next run. And that really feels like a gift. And so I guess it's part gratitude. There's a good deal of fear. I really don't want to mess this up. There's that happening. And then my other main driver is probably my students. I have students and postdocs who I am working very closely with. And that is just a thrill to watch them grow and develop and to have a responsibility to them. But also just the joy of working with them and, making breakthroughs together. Because you're right, many days are writing emails or copying spreadsheets. I spent a couple years of my career once hanging weights from springs and measuring how long, you just find yourself doing ridiculous things to get these big machines to work early in my career. But still that, I definitely have reasons to keep going.
Yeah. Can you talk about your particular contribution to Atlas for this Run 3?
Sure. My official title probably is not very transparent. I'm the data preparation coordinator for Atlas. What that means is it's the steps between grabbing the data and saying, okay, this is an interesting collision that we want to study, and then getting it to the point where people can actually do a physics analysis on it and ask questions like, did we find, is this potential dark matter? Is this the Higgs boson? All of that. So it includes the glamorous tasks of keeping track of the detector conditions as a function of time. What were the magnetic field strengths? What were the voltages? These databases we organize. It includes the visualization of the events. We have really beautiful event displays, colorful, large. They show you the interaction of particles traveling through the detector. It includes measuring how much data we've taken. You would think we would know how much data did we take in the last week. It's a non-trivial thing for us to actually determine with high precision. It's a number of those kinds of tasks that have to happen so that we can actually use the data that we take and extract the most physics out of it.
Yeah. And from that, how long does it typically take once you've got this massive amount of data, even with the help of AI that kind of categorizes it for you and organizes it for you, how long does it then take before you're doing presentations,
Yeah.
in front of, massive amounts of other physics out there?
It's an iterative process. So we have a goal on Thursday, on the 5th of July, at 4 p.m. local time. So that's in Switzerland. Very soon after that, we expect to have data that we take. I have a team that I'm working with that will try to find events within minutes to hours that we can start showing and displaying to people. But then, so it's everything from, okay, at the beginning, at the startup, we are so intensely going to be looking at the data to make sure that the detectors are functioning well, that anything that's broken, we can fix quickly because the data is very precious. We don't want to lose any of it. And then some analyses we're still working on. My group is still working on analysis from 2015 data. So it can take years and years and years to get the final precise measurements you want. So it depends on what questions you're trying to answer. And often you have to spin back and try again, get a little bit more data, try again, develop a new technique. Like you said, maybe we'll have an idea in a couple of years that will revolutionize the way we can analyze the data. We make sure that we have the tools to go back and run those kinds of analyses.
Yeah, that's got to be so exciting. I mean, this is coming up. That's why I had to have you on the show today. It was kind of a last minute thing, but I'm just so grateful that you were able to appear because we are really on the cusp of something that humans have never done before. I mean, this is run 3. Can you talk a little bit about how this run in particular is different, more expansive than it's ever been in the previous 2 runs?
So I'm going to pull an equation in with, I guess, without apologies. I think it's a pretty well-known one. E equals mc squared. This relationship that Einstein is famous for saying, if you have a certain amount of energy that you hand to nature, that energy can actually be used in the form of making massive particles. And the more energy you have, the more mass you have that you can play with. So the big step that we're making with this run 3 is really up in the energy that we're providing. We're getting the protons that we're smashing together to go even closer to the speed of light. Tremendous amount of energy when they collide. So that's one important difference. That means that the data that we took before, maybe we didn't have access to some processes because we just weren't there in terms of the available energy to make those processes occur and to see them. But the other thing that's really, there are 3 things. The second thing that's important is we're going to triple our data set. So the amount of data that we have is going to be increased dramatically, in part because the LHC has learned, the Large Hadron Collider has learned how to better deliver that data to us. So we'll have more data, which is also important. And then the third is a couple of new detectors have been installed. Some of them, the most exciting ones from my perspective, are the ones that let us actually select what we think is interesting. We have bunches of protons passing through each other 40 million times a second, which is a lot. And we can only keep about 1,000 a second to 10,000 a second. So the algorithms that we run right away to choose are critical, as you can imagine. One of the things we worry about is what if we're throwing away the data that is captured, that carries the answers to those mysteries. So we have some upgrades to our triggering system that helps us select interesting events. And that for me is some of the most exciting pieces of this because it expands what we have access to and the ways that we can search.
Yeah, absolutely. How do you, just as a researcher, as a human, how do you kind of seek inspiration for the work that you're doing? Because I feel like so much of the decisions that you make, you really come to you and from all of your massive amounts of work, like, do you spend time in nature? I know you have some work that you do with dance. How do you kind of down regulate your nervous system so that the inspiration, the good ideas really can come to you?
I think I personally need time just to be staring out into space. our house at where we live in Connecticut has the woods out and back, so I certainly enjoy walks. But even 5 minutes of walking from one place to another, if I am lucky enough to be on public transportation, which I am a lot around here, and sometimes, going into New York or out or different places, I'm a big stare out the window person, where I don't, I try to keep my brain not busy. That's been really important for me. Maybe that's, I don't know if that's not necessarily a revolutionary routine, but just moments of not pushing my brain, letting my day kind of organize itself in my head, and just having space for ideas. Because you can be too busy to be really creative. You can get in a rut. And I just need time to stare out the window. And sometimes I try to tell my students that sometimes the very best that you can do on an activity you're trying to do is to stare out the window for a few minutes. Maybe that's exactly what you need. So I try to just build that kind of time into my day.
Yeah, that's huge. And honestly, like after this all happens, and how long does it run once it gets going?
This is a marathon. This is not a sprint.
Yeah.
So it's a 24/7 operation. We'll be going actually just for a couple of months here through the end of November, and then shut down for a couple of months when electricity is particularly expensive here in Europe, which also gives us time for some repairs. And then we get going again in the early spring, and we'll run for a number of months. So we have a cycle of, 8 months on or 9 months on, depending on the year, a month or a couple months off. Of course, the running of the detector is not the running of our brains, because like I said, we're still analyzing the data we have in hand. We're going to start analyzing data as it comes in. So there's a break from the operational perspective, but not from the work perspective. And that's something to be aware of, particularly since the holidays in the US and Europe don't always overlap. You have to watch yourself a little bit.
Right.
You don't always get those opportunities to take an actual break. Yeah.
Wow. So, I mean, we're almost to the end of time, but I'm just really curious, like, what are you feeling? What is the energy around CERN right now? What are you personally feeling? Is it a lot of anticipation? Is it a lot of, I don't know what's going to happen? Like, what's the vibe there?
It's an interesting vibe. The schedule is so dynamic. There's actually a lot of uncertainty about what's going to unfold at what pace. It's the pace that's uncertain over the next couple of weeks. We don't know what problems we're going to be facing from the detector. There are some things that we know are going to be tricky, but we know we're going to have some surprises. I would say it's a combination of anticipation, definitely nervousness about the areas that I'm responsible for, not solely responsible for, but working with. But I also have a lot of confidence that whatever is thrown at us, we're just going to put one foot in front of the other and make progress as quickly as we can. So I think there's a confidence that we're going to extract the most out of this data that we can as soon as we can. And I think we're ready. This has been a long time coming. So the date has been looming large. Yeah. It's a little unusual in the field to have a definite date so far in advance that we've been aiming for. So that's a factor too, that, okay, it's July, we're ready. Let's go.
Yeah, absolutely. It's kind of like Christmas morning, I'm sure, for everybody.
Yes. Yeah.
To kind of round everything out, what would you say to the average woman listening to this? I wanted to have you on the show because I feel like, as mothers especially, this is something so amazing for us, for the world, for our children. I mean, we're really headed into unknown frontiers, and that's why I really wanted to have you on the show. What would you say to the woman listening to this who's wrapping her head around everything that's happening and is going to come into our knowledge field? What would you say to her and just the future of the world?
Wow. Well, I would say, first of all, there's a sense there aren't a lot of women in the field of physics. I guess it's 20% about on Atlas, so 1 out of 5. And there's definitely a sense of camaraderie among the women. I would say I have gotten so much support throughout my career from women. And I feel a responsibility in my career to mentor and represent, be as competent, be as accomplished as I can also. So I feel some sisterhood in my work that has really been critical for me throughout my career in very real ways. So my first thing would be thank you. Thank you also because we're taxpayer funded. So, I would want to communicate that we're good stewards of the resources that we have. We're working hard and really grateful for that. The last thing I would say is that the universe, from what I've learned in physics, it really is so surprising. Physics is the gift that just keeps giving. In terms of quantum mechanics, special relativity, things don't behave the way we would expect, just moving around and pushing objects around us. It's shocking when you learn about how things actually behave at the particle level. And I really think that some of that really beautiful, surprising physics is accessible. There are books out there. It's worth talking about. It's worth thinking about. And I hope that people have that sense of wonder from the universe and how exciting it is to try to make forward progress and access more of it.
Yeah, well, we're definitely getting that from hearing you today. I think the interest will certainly be sparked, especially as we head into next week. Dr. Demers, where can our listener find out more about the work that you're doing and have done, which is also fascinating, all of your papers? And then how can we follow along for the 5th?
So there is a website for the 5th. There's actually going to be a broadcast that starts 4 p.m. local time at CERN. So there's a link available. The CERN media website is going to be there. I actually am one of the few people who's going to be interviewed in the Atlas control room. So I'm still thinking about what I'm going to say and getting ready for that. So people can follow along live for our first 2 hours of running, which will be quite exciting. But I think, the CERN website, the Yale physics website, there's a lot of resources out there. We have this wonderful particle adventure website, particleadventure.org, I think, where you can learn about what particle physics is, what we're trying to do, and some of the physics mysteries that we're tackling. Plus so many books that people have written, for lay people about the Higgs boson discovery. There's tons of ways to dig in. I don't know. Yeah, I'm happy to provide any links like that, but people could even just Google CERN and find all kinds of wonderful resources about Atlas and the work.
Yeah, absolutely. And guys, that will all be in the show notes, of course. Dr. Sarah Demers, thank you so much. I'm so excited for you and what's happening. Thank you for taking time out of your very busy schedule to spend some time with us.
Thank you. I really appreciate it.